Hi everyone, welcome to the episode number 21. In this episode, we will see a very interesting problem from recursion and backtracking. This is the n queen problem. And if you solve this problem, if you understand this problem, which obviously you are going to after watching the complete lecture with patience, you will master recursion. You will be able to solve any other problem in recursion, okay? Now, the problem statement is very simple here. The problem says that you are given a chessboard of n cross n dimension and you have to place n number of queens on this chessboard, okay, such that those queens do not attack each other. Now, you must be aware of the fact that where all does a queen attack, and if you don't know that, let me give you a slight example of it. So let's say if we are placing the queen at this position, let us denote it by I comma j. Okay, so this is the cell where I'm placing the queen. Now this queen is going to attack in the upward direction, it is going to attack in the downward direction. Okay, so basically it is going to attack anything, any piece which is in the same column. So we cannot place any other queen in the same column, right? This queen is going to attack in the leftward and in the rightward direction as well. So anything in the same row will be attacked by this queen. So we cannot place any other piece or any other queen in the same row. Okay. Now this queen is going to attack in this diagonal, okay, in this diagonal. So anything on this particular diagonal will be attacked by the queen. So we cannot place anything in this particular diagonal as well. Now there's one more direction left. So this direction and this direction. So basically we cannot place anything on this particular diagonal as well. So these are the 8 directions where the queen is going to attack, and we cannot place any other queen in all of these 8 directions, right? We have to place 4 queens on a 4x4 chessboard and 8 queens in on an 8x8 chessboard, right? So on n cross n chessboard we have to place n number of queens. Now let me show you the correct configuration, that how are we going to place these queens, right? Before that, let me show you a wrong configuration as well. So a wrong configuration could be queen over here, queen over here, queen over here, and a queen over here. This is a wrong configuration. Why? Here 2 queens are attacking each other. They both are attacking each other, right? So this is not a correct configuration. Let me talk about a correct configuration now. So this will be a correct configuration, this one. Now here we have placed 4 queens and they are not attacking each other, right? This is not attacking any other queen, this is also not attacking any other queen. You can just verify it, you can pause the video and verify it. So what could be the other configuration, other right configuration? So let me just paste a chessboard over here. This is a 4x4 chessboard again. Let me make another configuration. So if I place a queen at this place and here and here and here, this is also a valid configuration. Here we have 4 queens in a configuration such that they are not attacking each other. So this is also a valid configuration. We have to generate both of them and we have to return both of them as the answer. This is the question. Okay. All right. Now how are we going to do this? So basically one thing that we can identify is we can only place 1 queen in a row. If we place more than 1 queen in a row, they are going to attack each other, okay, which will be a wrong configuration. So that's why only 1 queen in 1 row. Okay. Now, is it necessary to place 1 queen in every row? Can we skip a row? Can we simply place 0 number of queens in a row? So the answer is no. Why? Because how many queens do we have? We have n number of queens. How many rows do we have? We have n number of rows. So if we skip a particular row, and let's say there are n queens, if we skip a particular row, I will have to put more than 1 queen in any other row, right? If I keep 1 row empty, I will have to place more than 1 queen in any other row, which is a wrong configuration, right? So we have to place exactly 1 queen in every row. Okay, 1 queen in every row should be placed. So now the question reduces to place n number of queens in n rows. Simply place n number of queens in n rows. All right. So we can solve it using recursion very easily. We will again see those 4 steps that we saw in the lecture number 6. First of all, what are we going to do? How are we going to solve it? So this is the chessboard. We will be solving it in such a way that we will be filling each row. Okay, we will start from the first row. We will keep filling the rows one by one. Now let us say I am in the ith row. I am in the ith row. I am talking about the ith row. I need to fill this. So if this ith row is equal to 6, this is the 6th row. Okay, if it is the 6th row, it basically means that all the rows above this has been already filled. Okay, all the rows above this has been already filled. Now if I want to place anything in this 6th row, first of all I need to identify the places which are safe for the queen to be placed, right? I cannot simply place it anywhere because there are already queens, there are already rows which contains queens above this, right? So I need to respect them because they are already placed. Now the next queen, the sixth queen which I am placing, it should be such that it do not attack any of the previous queens. Okay, so I need to identify that safe position. So for example, let's here take the queen here. Now let us say I'm talking about this particular row, I is equal to 1. So what all safe positions do I have here? This is not safe, this is not safe. Why? Because these both positions will attack the previously placed queen, so we cannot do that. So that's why this is the safe position and this is the safe position. So these are the two safe positions that we can currently place our queen at. Okay, so what I will do is I will basically place the queen at one of the safe positions. Okay, let's say if I'm placing the queen over here, and I will ask recursion to do rest of the task. Okay, I will ask recursion to do rest of the task from I plus 1th row till the end. Okay, similarly place one queen in every row, and before placing just verify that what all positions are safe to place. Okay, that's what I'm going to do. So it is recursive in nature. Why? Because the problem statement is now to place one queen in every row. Okay, so we will handle placing the queen in one row and we will ask recursion to place it in rest of the rows. Okay, so it is recursive in nature. Now the next thing is small task that I need to do. The small task that I need to do will be to place the queen in the current row. Okay, to place the queen in the current row. Alright, so for that, first of all, I will have to verify, I will have to get the safe positions, and after once I get the safe positions, I will basically place the queen in one of that safe position and ask recursion to do rest of the task. So here we have two safe positions. I will place the queen over here and I will ask recursion to do rest of the task from here. Okay, then after that, after exploring this possibility, the other possibility is this, right? The other possibility is to place the queen at this place. So I will also explore that because I want to generate all the possible answers, right? As we have already discussed, we have to generate all the possible configurations. So we cannot simply stop by getting one of the possible configurations, right? So we have to generate all the possible configurations. That's why we already explored one of the possibility by placing the queen over here and asked recursion to do rest of the task. Now recursion is done doing its task. So undo the change. Just remove the queen from here and now place it somewhere else. Okay, undo it, remove it from here, now place it somewhere else. Basically means the next safe position. So place it over here and then ask recursion again to do rest of the task. Okay, now let us say if I have 7 number of safe positions. So I will do this 7 times. I will place the queen at the first safe position and I will ask recursion to do rest of the task. Then I will remove the queen from that safe position and place it to the next safe position. Then again I will ask recursion to do rest of the task. Okay, then again I will remove this from the second safe position and place it to the third safe position, and again I will ask recursion to do rest of the task, and I will keep doing this. And what does it mean by removing it? The backtracking step. As we have learned in the previous lectures of recursion and backtracking, it is the backtracking step to remove the queen, right? So that's what I'm going to do. So basically what I will do is I will go to each row one by one, and in the current row, let's say if I'm currently standing in the ith row, I will look at all the possibilities and I will find the safe options, that these are the safe options. Okay, now to find the safe options, we will do slight calculation and I will tell you very soon what that calculation is going to be. So let's say I figured out that there are n number of, not n, let's say there are 5 number of safe places, right? So I will try to place the queen in each of those safe places one by one, and I will ask recursion to do rest of the task one by one. Okay, that's what I'm going to do. And where am I going to stop? The fourth point, the base condition. Where am I going to stop? I'm going to stop when I filled the chessboard. And how will I know that I have filled the chessboard? My I will become equal to n. Okay, my I is denoting the row, 0th row, first row, second row, third row. When I becomes equal to n, basically I filled up the chessboard, and then I will save the answer. This is the chessboard that I have made. This is the configuration of the chessboard which I have created. Save it. Okay, that's what I'm going to do. All right. Now, how to figure out the safe position? So let us say I'm talking about a particular row. Let's say I'm talking about this particular row. So in this particular row, if I want to place a queen, how will I know that what all positions are safe? So we will start going to each one of these positions one by one. So let's say if I'm talking about this position, to verify that if it is safe or not, what I'm going to do is I'm going to see in the upward direction. I will run a for loop in the upward direction, and I will see that if there are any queens in this particular column, okay, if there are, then it is not a safe position, as simple as that. Okay, then I will go to this direction, diagonally upwards. Okay, right diagonal upwards. So I will run a for loop again. So I will see that if there are any queens placed. If there are, then we are going in the wrong direction. I mean, this position is not safe. Okay, so stop. Then we will also check for this particular diagonal. Okay, here this diagonal doesn't exist. For this position this diagonal will exist. So here the upward direction will exist, the right diagonal, the left diagonal, all these three things will exist. So we have to check in all of these three directions. We had 8 directions, I agree, we had 8 directions where the queen can attack, but we only need to check for the 3. Why? So basically, first of all, we don't have to check for the horizontal column, I mean the horizontal row. Why? Because we are already placing one queen in every row, so that's why we don't have to check it horizontally. Okay, and we don't have to check it in the downward direction. So in the downward we have these 3 directions, we don't have to check in these 3 directions. Why? Because we are filling the chess from up to down, from the top to bottom we are filling the chessboard, right? So we don't have to check in the downward direction. So that's why only these 3 directions are left: up, right and left diagonals. Okay, these are the 3 directions that I will have to check for every particular cell. So I will get to know that what all cells are safe to place the queen. I will place the queen there and I will ask Recursion to do rest of the task, and I will then remove the queen from here. Then I will go to the next safe position, I will place the queen there, I will ask Recursion to do rest of the task, I will remove the queen from there, and so on. This way I will be able to generate all the possible answers. Now shall we start coding this? Things will become much more clear once we start coding this. Okay, so let us go, let us start coding this. But before that let me quickly explain you one more thing. Okay, so we saw that we can check for a safe position with the help of the for loops, right? With the help of the for loops we can check the safe positions, but we can do slight optimization over that as well. Okay, we can do slight optimization over that as well. How we can do that? So basically, if I want to place a queen at a particular, let's say a particular column, first of all I need to make sure that nothing is there in the same column. Nothing is there in the same column. So basically there are going to be n number of columns, right, from 0 to n minus 1. So I can create an array. Okay, I can save this. This is not an array, this is a triangle. I can create an array. This array will be of size n from 0 to 3, 0, 1, 2, 3. Okay, now this array is going to, each particular cell of this array is going to denote one particular column. Okay, so the column number 0 is already occupied, I will mark this as 1. If let's say if the column number 1 is occupied, I will mark that as 1. So whatever columns are already occupied in the board that we have filled so far, I will keep marking them as 1, so that if I want to check, instead of running a for loop in the upward direction, I will be simply able to check. Let's say if I am talking about this position, here the column is 0, 1, 2, here the column is 2. So I will simply check in this particular array, what is the value placed at this index 2? It will be 0, right? It will be 0. That means it is not filled. So it is a safe. We cannot say if it is a safe position because there are other things as well apart from this. There is this diagonal and this as well. But in case if it is equal to 1, simply it means that this place is not safe. Go to the next place and try to see if that next place is safe or not. So basically 3 things should be there. One is this, it checks for the column. Then we should have something for this diagonal as well and for this diagonal as well. Now for these 2 diagonals, let me show you an example. So let us draw another chessboard over here. Okay, let's say this is the chessboard. Now in this chessboard I will mark the indices 0, 1, 2, 3, 0, 1, 2, 3, and if I start taking the summation, so the summation here is 0, summation here is equal to 1, summation of row and column, right? Summation of row and column. So the summation of row and column here is 4, summation of row and column here is 6. Okay, summation of row and column here is equal to 1, here is equal to 2, here is equal to 3. Summation here is equal to 3, here is equal to, here it is equal to 4. Okay, summation of row and column here is equal to 2 plus 3, 5. Here it is equal to 2 plus 3, 5. Here it is equal to 1 plus 3, 4. Here it is equal to 2 plus 1, 3. Here it is equal to 0 plus 2, 2. Here it is equal to 1. Okay, and here it is equal to 6, not 6. Here it is equal to 3. Okay, so this is the summation, and what do we get to know from this summation? We get to know that everything on this particular diagonal, so everything on this particular diagonal, here it is equal to 2 actually, not 1, here it is equal to 2. So everything on this diagonal, this and this, they are all equal. Okay, they are all equal, right? So this diagonal can be represented by index. Okay, this is 0, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. Okay, this is 6. So basically each one of this diagonal can be represented by one of the index, so we can basically convert them into an array as well. So we will have an array of size 0, 1, 2, 3, 4, 5, 6, right? An array of size 7. All right. So basically, if anything is there on the diagonal which is denoted by 0, we'll simply mark 1 there. If anything is there, any queen we have already placed in the past at, let's say, this particular position, so this is going to be marked with the index 3. So you'll mark 1 here. So this way we can create a particular array for this diagonal as well. Now what about the other diagonal? What about these diagonals? Okay, so for these diagonals it is a little bit tricky, but again let me take an example and show you. So again taking a 4x4 chessboard, and yeah, so let me do this, row minus column. Okay, row minus column plus n minus 1. N minus 1 is constant, row minus column will change. 0, 1, 2, 3, 0, 1, 2, 3. So it is the row minus column is, this is the row, this is the column. Row minus column is equal to 0 plus n minus 1. And what is n minus 1? N minus 1 is 3. So it is going to be 3. Okay. Row minus 1 is minus 1 here. Row is 0, column is 1. So it is minus 1. Minus 1 plus 3 is 2. Okay. Here it's going to be 1, here it's going to be 0. Similarly here the row minus column is going to be 1 plus n minus 1 plus 3 is equal to 4. So 4, 3, 2, 1. Okay. This is how it is going to be. Then 5, 4, 3, 2. Okay. 6, 5, 4, 3. So this is going to be the entire matrix. You can just verify it. So each one of these cells contains the value r minus c plus n minus 1. Okay, r minus c plus n minus 1. So now we can see that these diagonal, okay, this was the diagonal that we were talking about, right? So these diagonals have the same value, so we can denote them by index of an array. Okay, so this was for the this is the current one is for the left diagonal. Okay, left diagonal. This was for the right diagonal, and this particular array was for the column. Okay, so we are going to basically have 3 of these arrays. Now 3 of these arrays will help us a lot in finding the safe position. Okay, we will see the optimization, we will see the previous solution as well and the optimized solution as well, so don't worry about it. One more thing that I want to explain before going to the chessboard, before going to the coding part is the recursion tree. Okay, so let us go and see the recursion tree as well. If you are not able to understand this optimization step, you can just re-watch the video again if you are not able to understand it. Let me draw the recursion tree over here. So as you have seen in the past, in all the previous episodes, this is going to be very easy for you. It's going to be a cakewalk. I will start with the row 0. Okay, starting with the row 0, how many safe positions do I have? Here we have 4 safe positions, right? All these positions are safe because we have no other row filled. Okay, so everything is empty yet and all these positions are safe. So we have 4 options to fill the first queen. We will go with the first option. All right, let us go with the first option. So the first option is going to be placing the queen here. All right, here I is equal to 1. When I is equal to 1, we are basically talking about the second row. And in the second row, what all are the safe positions now? This is not safe, this is not safe, because these 2 positions are attacking the previous queen. Okay, this is safe, this is safe. Let me go with the first safe position. So the next chessboard would look something like this. First queen here, second queen here. Okay, now from here the I is equal to 2. When I is equal to 2, we are talking about the third row. In the third row, what all are the safe positions? It is not safe, it is also not safe because of this, it is not safe, it is not safe. So all these 4 positions are not safe, which basically means that we are not able to place the third queen in the third row. We are not able to place it, and we cannot afford skipping this row. Why? we are supposed to place at least and exactly one queen in every row. Exactly one queen should be there in every row, and here we are not able to place it. So what does it mean? It means that we have done some mistake in the past. Okay, we have done some mistake in placing the previous queens, and this mistake is now affecting us a lot. That's why I cannot go beyond. I should stop. Okay, stop at this particular place and return from here. Okay, return from here. But while returning, I should undo the change. What change did I do? I basically placed the queen at the first safe position. I should undo that. Okay, by placing a queen there, I was not able to generate the configuration. I was not able to get the correct configuration. Now it is time that we should check by placing at the second safe position, and when we are placing at the second safe position, we should remove the queen from the first safe position, right? The undo step, the backtracking step. Okay. Now let us go to this direction, and here if we go to this direction, we will be having something like this. First queen here, second queen over here. Okay, second queen over here. Now in the third row where I is equal to 2, do we have any safe place? No, yes, no, no. This is the safe place. Only one safe place is there, so we can place the queen over here. So if we place the queen at the safe place, we will get a configuration like this. Here we have queen, queen, queen. Okay, I is equal to 3. When I is equal to 3, we are talking about the last row. Here let us see what all safe positions do we have. Safe, no, safe, no, safe, no, safe, no. We don't have any safe positions in the last row. So again we failed. Again we failed to generate the configuration. And why did we fail? Because we made some mistake in the past. Okay, we should undo that mistake. So we should go return from here. While returning, I will remove this queen. Okay, so we'll get this back. From here also we will return. Okay, we'll remove the queen. From here also we will return, and we'll remove the queen. Everything is wrong. Going in this direction itself was wrong. So that's why we kept removing it, and again we reached to the first step. Alright, so the camera again turned off. I don't know why. Alright guys, now you will have to understand the remaining part without looking at me, because the camera is not working. So we saw that in this particular direction we were not able to generate any possible answer. Now let us try to basically generate the answer going in the other direction. Okay, so for that let me quickly copy this chessboard. Okay, let me paste it over here. So here we will be marking this position, right? Here we'll be marking with this position. In the last in this direction we went by selecting this position. Now we will be selecting this position. Okay, now again when I is equal to 2, sorry, I is equal to 1, we are talking about the second row. Now in the second row, what all are the safe positions? It is not safe, it is not safe, it is not safe, it is safe. Okay, let us select it. Let me paste it. After selecting it, we will basically get this configuration. Okay, talking about I is equal to 2, the third row, we have this as safe position, this not safe, this not safe, this not safe. We only have one safe position. We will go with this particular safe position. So let me paste it over here. Yeah, so this is already there, this is already there. Now we will place the queen over here. Now talking about the last row, this is not safe, this is not safe, this is safe, this is not safe. So we are able to place a queen over here. So if we place a queen over here, what will we get? We'll get this one. So the configuration would look something like this: queen, 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 and queen. So yes, this is one of the correct configuration. Okay, this is one of the correct configuration, and because now I is going to be equal to 4, okay, I is going to be equal to 4, we will be saving this configuration. We will hit the base condition, correct? Just save this configuration and then backtrack. Okay, while backtracking you will undo, you will remove all these queens from here. Okay, and while backtracking we will try to explore other possibilities. Now you can continue doing this recursion tree, you can continue following this recursion tree, and you will be able to generate another possibility as well. I will not be drawing it because it will become very huge. So you got the hint, right? Okay, now you got the hint how the recursion is going to work, and this will be the recursion tree. Now let us talk about the space and time complexities. So first of all, what is going to be the depth of the recursion tree? What is going to be the height of this recursion tree? So the height will be equal to the number of rows, n. That will be the height of the recursion tree, and we know that height of the recursion tree denotes the space complexity. Okay, the big O of n will be the space complexity because of recursion. Okay, but we know that to generate the output, to generate the answers, we need to store these n cross n chessboards, right? So n square space will be used. Okay, n square space will be used to store them. And let us say in the final answer we have let's say 5 correct configurations. In the case of 4 cross 4 we will have only 2 correct configurations. So let us say we have n cross n chessboard where we have 5 correct configurations. So we are going to save all these 5 possible configurations and return them. So we will have 5 chessboards of n square size. So the complexity will be n square, big O of n square. This will be the space complexity to output, to return the output. Okay, so when the interviewer is asking you to return the to tell the space complexity just because of recursion stack, it will be big O of n, and when he's asking you the overall space complexity, that will be n square. Now talking about the time complexity. So yeah, so let's say how many rows do we have? N number of rows. Now we are filling, let's say we are filling the first row. After filling the first row, we are going to the second row. In the first row, how many options do I have? N options. In the second row, how many options do I have? N minus 1 options at most. At most n minus 1, less than that. Okay, but let us talk about the worst case, n minus 1 options. Why? Because one column is occupied. One column is occupied by this particular queen, the first queen. Okay, let us write it down here. So initially we have n number of options and placing the first queen. Then we will have n minus 1 number of options placing the second queen. Although we will have less than n minus 1, but just in the worst case, okay, we are taking the upper bound to calculate the worst case complexity. Then we will have n minus 2 options, n minus 2 options in the third, placing the third queen. Placing the fourth queen, we will have n minus 3 options, and so on till we have, at last we have only one option, placing the nth queen. Okay, so this will be the complexity. So n into n minus 1 into n minus 2 n into n minus 3 and so on. So this will be n factorial. This will be the time complexity. Okay, this will be the time complexity. All right, so this is what you can do. Now you must be thinking that why are we not calculating the number of nodes here, because we have always done this in the past, that when we want to find out the time complexity, we always calculated the number of nodes. Okay, so you can even do that. So instead of visualizing it the way that we did right now, what you can do is you can visualize in terms of number of nodes as well. So initially let's say we have 4, so initially we will have 4 options. Okay, now all of these 4 options will have 3 options each, right? They have 3 options each. How 3 options? So basically we have 4 columns, right? So initially we will be having 4 options, but then one of that option, one of the column will be occupied by one of the queen, so only 3 columns will be remaining. So 3 options here. So each one of them, let us say each one of them have 3 options. Okay, so how many nodes are there in the first level? 1 node. How many nodes are there in the second level? 4 nodes. How many nodes are there in the third level? 4 multiplied by 3 nodes. Now in the next level, all of these will have 2 options each, right? All of these will have 2 options each. So this will be equal to 4 multiplied by 3 multiplied by 2, right? So it is kind of factorial only. So at the last level you will see that you have n factorial number of nodes. Okay, so that's how so it will be like n factorial plus n minus 1 factorial and so on, which can be simplified as n factorial only. Okay, because n factorial is much larger than all of them, right? So this is going to be the number of nodes, this is going to be the time complexity, and we already discussed about the space complexity. To calculate the space complexity, we always look at the depth of the recursion tree, the height of the recursion tree to calculate, and apart from that we also look at the output the output that we want to generate. So both of them we have to explain separately, that this will be the space used by recursion and this will be the space used by output. Whichever is maximum is the final space complexity. All right. When we look at the time complexity, we often look at the number of nodes in the recursion tree, and if you are able to evaluate it, it is very good. And if you can find a simpler way, just as we did over here, if you can find a simpler way, you can even evaluate it using that simpler way. Okay, but like as a thumb rule, always the number of nodes are going to be the time complexity. Okay, so this is it. Now let us start coding this. We'll create a function void help. Okay, void help, and it's going to contain I. This will denote the row, that this is the ith row which I am filling. Then I should also have a vector of int. Vector of int, basically it is a 2D array. So this 2D array will contain the configuration of the chessboard, and if you read the question properly, right, the configuration of the chessboard is something like this. So basically there are n rows and n columns, and 0 represents empty spaces, 1 represents the queen. That's what I'm going to do. This is the chessboard, and then we will have answer. So how are we supposed to store the answer? So let us say this is one of the possible configuration that I want to generate. So if I want to store this, I should flatten this. So basically after this row I should place this row. So I should flatten. After flattening, it will look something like this. Okay, so from here to here it is the first row, from here to here it is the second row. Okay, from here to here it is the third row, from here to here it is the fourth row. So after flattening, it will look something like this. So I will show how we can flatten this. It will be very simple, but finally we have to return a vector of int answer. Okay, vector of int answer. All right, don't worry, just have patience. I will explain each and everything. So first of all, what I need to do is I need to find a safe position for int j is equal to 0, j is smaller than n, and j plus plus. Going to each and every column, I need to find the safe position. So if is safe, let me write a function is safe I comma j. If this position I comma j is safe, I am creating another function for that. That function basically will return me true or false. If it is a safe position, it will return me true. If it is a false position, it will return me false. So depending upon that. Now here I comma j, and what else do we need to pass? We need to pass the chessboard as well. Chessboard. Okay, why do we need to pass the chessboard? Because a few rows of the chessboard we have already filled, so we can only tell whether the current position is safe or not if we look at the previously filled rows, right? So if it is a safe position, obviously we can place a queen at that position. Okay, so let us place the queen at that position. So chessboard of I comma j is equal to 1. This is placing the queen. Okay, 1 denotes queen. After that, we will ask recursion to do rest of the task. So by doing rest of the task, I mean go to the next row and do the task from the next row. Chessboard, then answer, done. After coming back, undo the change which you are doing. Basically remove the queen from here. Remove the queen and place 0. Now, why do we need to remove it? So one possible case could be, let's say we are asking recursion to do rest of the task here. Recursion has done doing rest of the task, and it might be possible that it found out few of the possible configurations, and those possible configurations are saved in the final answer. Okay, but after coming back, I need to find out other possible positions as well, other possible configurations as well. So for that, I need to undo the change and place the queen at the next safe position. Okay, this is the backtracking step. Backtracking done. And I guess that's it. One more thing, base condition. If I is equal to n, this is the base condition, and if it is the case, then answer dot pushback. I need to push back in the answer, but before pushing back, I need to flatten the given chessboard, right? I need to flatten it. So how to flatten it? First of all, let me take a vector of int temp, and then for int j is equal to 0, j is smaller than n, j plus plus. For int, I'm basically going to each and every element in this particular chessboard, and I'm basically flattening it. Okay, so k is equal to 0, k is smaller than n, k plus plus, temp dot push back the value chessboard of ij. Alright, after flattening it, I should save it inside the answer and then return. Done. Okay, so this is it. I need to write this safe function is safe as well. So that will be a boolean function. Bool is safe. So here I will have int I, int j. These are the positions where I want to basically place the queen. So I need to know what is the previous chessboard. Okay, previously filled chessboard. Then I will make use of those for loops. So first of all, let us check in the upward direction. Okay, let us check in the upward direction, and I'm taking I should do I minus minus, right? I should do I minus 1, but I'm taking a temporary variable, temp I. This will be equal to I. I don't want to disturb the original I that we have. So temp I, while this temp I is greater than equal to 0, okay, till then we can just check, keep on checking. Okay, so if chess board of I comma j, if it is equal to 1, basically if there is a queen, then return false. As soon as you basically see a queen, return false. You're going in the upward direction and you're checking if this direction is safe. If you find a queen, then it is not safe, return false. Okay, this is going in the upward direction. Now let us go to the top right. Okay, top right diagonal. So if I want to go top right diagonal, I should do I minus minus because I'm going upwards, and I should do j plus plus because I'm going rightwards. Okay, top right. So int temp I is again is equal to I. So you can see that I basically had to create a temp I again. I had to reinitialize temp I again with I. That's why I was not disturbing the original I. Okay, I need to reuse it again here. So temp I is equal to this, temp j is equal to j, and while temp I is greater than equal to 0, and temp j is because I'm going upward, that's why I'm checking for 0 here for I, and for j, because I'm incrementing j, I should make sure that this is, while this is smaller than equal to n minus 1. Okay, till then if chess board of I comma j, if it is equal to 1, then return false. Okay, return false. So this is checking in the top right direction. Now checking in the top left direction. So again temp I is equal to I, temp j is equal to j, while temp I, because I'm going in the upward direction again, greater than equal to 0, and temp j, because I am now going in the leftward direction, I should check the same condition, temp j is greater than equal to 0. Oh, one more thing I forgot. I need to basically here I need to keep decrementing. Here I need to keep decrementing temp I minus minus. Okay, and in this one I should, because I'm going in the top right direction, what I should do is I should do temp I minus minus and temp j plus plus. Okay, and while going in the leftward direction, temp j is greater than equal to 0, both of them greater than equal to 0, if chessboard of I comma j, if it is equal to 1, then return false. Okay, temp I minus minus, temp j minus minus, both of them minus minus. Okay, after coming out of these 3 tests, return true. This is a safe position. Okay, so if either of these 3 are returning false, that means it is an unsafe position, and finally if we return true, that means it's a safe position. All right, now what do we have to do is we have to create answer vector of int answer, and then we need to create a chessboard as well. So vector of int, that will be of size n cross n. Okay, vector of int chessboard n comma size n comma vector of int n comma 0. So basically it is a n cross n chessboard of size, I mean filled with zeros, means all the positions are empty initially. Now we need to call this help function starting with I is equal to 0, n I is equal to 0, n chess board and answer. Finally return the answer. Okay, let us see if there are any errors. There are. Temp j was not declared, so here int temp j. Bool in function bool is safe, n was not declared, so I should pass n as well. Okay, I should pass n as well. So is safe is also taking n. So where do we need is safe? We need is safe at this place, taking n. Okay, push answer dot push back. Chessboard was not declared. This is 45. Chess chessboard, chessboard. Any other errors? Segmentation fault. Why are we getting a segmentation fault? Because why are we getting a segmentation fault? Are we overshooting any place? So this is correct. Temp is greater than equal to 0, and this is minus than equal to this. This is also correct. Here, oh, it should not be. It should be temp I and j. Here it should be temp I and temp j. Temp I, temp j, but I don't think it is something. Okay, it is giving us one of the correct answer. Let us see other segmentation fault. Why are we getting other segmentation faults? So vector of in temp I k is equal to 0, k is more than k plus plus. Here we need to fill j and k. Okay, here we need to fill j and k. Yeah, so we are getting correct answer. Your output, what is this? We are getting correct answer for this. Let me submit this. And it got accepted. Okay, it got accepted. It is a correct solution. You can have a look here. So the Java code and other languages code will be available in the description. This save function is very simple. Okay, this save function is very simple. You need to check in 3 directions only. In the upward direction, where you will only do temp I minus minus. In the top right direction, while going top right, you have to do temp I minus minus and temp j plus plus. While going in the top left direction, just do temp I minus minus, temp j minus minus. Okay, this is what you need to do. This save function is very simple. You don't have to even remember this. It's going to be very simple, but it's time consuming. It is taking big O of n time. So that is what I want to remove. I will remove that very soon. Don't worry. I will do it constant. Okay, we'll do it constant using those 3 vectors which we talked about, right? Using those 3 arrays. So one array will be for column, one array will be for the one diagonal, other array will be for the other diagonal. Okay, we'll do that. So don't worry. Now this is the main recursive function. This is the base condition. If I is equal to n, basically save the answer. Before saving it, just flatten the answer and then save it. Okay, the question only demands us to flatten it. Otherwise there was no need of flattening it. The interviewer will not ask you to flatten it most probably, but the question demanded us, so that's why we flattened it and then saved it. This also you don't have to remember anything at all. The only thing that you need to remember is how to solve questions recursively, right? You need to do a small task. Small task is to place the coin. Okay, first of all, find the safe positions, place the coin, ask recursion to do rest of the task, undo the change, then put a base condition. That's it. Okay, this is the entire code. This is a very small code and it's a very simple code. Now let us try to improve this. Let us try to remove the usage of this is safe. Now we need to get rid of this save function. So if I want to get rid of this save function, what I need to do is I need to use those 3 vectors which we talked about. Okay, one vector will be denoting that which columns have been already filled. So it will be of size n, initialized with 0. One column will be for the top left diagonal. So if I talk about the top left diagonal, we saw that we had an equation like this. I minus j plus n minus 1, right? So it used to denote one of the diagonal. So let us take this of size 2n, initialize it with 0. Then one more top right diagonal. So for top right diagonal, we saw that I plus j is constant, right? I plus j is constant for the same diagonal. So this, let us also take it of size 2n, initialize it with 0. So these three vectors are going to help us. Okay, column, top left, top right. These are the three columns. These are the three vectors. Let me just take them over here as well. Vector of int columns, comma vector of int TL, vector of int TR. Okay, left and right. And we also need to pass them over here, column TL TR. All right, we initialize them, we pass them from here, and now instead of using this is safe, I can simply check column of j. If this is equal to 0, basically means that if this position is safe, and TL left. So for the left side we had I minus j plus n minus 1. So this used to be constant. So this will denote a particular top left diagonal, and if it is equal to 0, so basically this should also be equal to 0. Okay, and TR of I plus j, this should also be equal to 0. If these three things are 0, then yes, we are good to go. We can put one of the coin on this particular position. Now we should also do this. We should also mark these positions as unsafe. Okay, for the future coins we should mark them as unsafe. We should mark them with 1. But when we are backtracking, so we should also mark them as safe again, because now we are removing the queen. So after removing the queen, these positions will be safe again. Let me run this. See, we are getting the correct answer. We are not even using the isSafe function. We will remove it. Simply remove it from here. Now we have a compact code, a very small compact code, and we are just using these three vectors. And then if we submit this, we'll get the correct answer. We got the correct answer. Now what you need to do is basically take a pen and paper, try to draw the matrix, n cross n matrix, and then this one is very easy to understand. This column thing is very easy to understand. Now this TL means top left diagonal. So in the top left diagonal, this I minus j plus n minus 1, this is going to be same for every cell in the same diagonal. Every cell which lies in the same diagonal, it's going to be same, and you can draw and basically verify it. I have already done that in the lecture, but if you don't remember it, you can just make a matrix and then try to put this value in every cell. You will see that every top left diagonal, every cell in the same top left diagonal will have same value. Okay, so we will be able to distinguish each one of the top left diagonal separately with the help of an index. Similarly for the top right diagonal. Okay, this I plus j is going to have same value for all the cells in the top right diagonal, and every top right diagonal will have a different value of this. Okay, and that's how we will be able to distinguish them. Okay, so just do this activity, try to submit this code, and I am really exhausted by teaching this lecture because I taught it in very depth. I hope you are able to understand it. Let's meet in the next lecture. Bye bye, take care. Do like the video before going to the next one. Bye bye.